this is the summarization step before we further compute the derivative with respect to the kernel width. Let us put the computation we have done before using some utility functions and make the style consistent. So let's redo the convolution function in a proper way. Now we have, let's call that convolutional 2, which means the second function as well as two-dimensional. Well, we have the width, the height and the width to be the shape of x. Then let's see the kernel height and the kernel width to be the shape of kernel. Then the output will have the size of the height of the input minus kernel of the input and plus 1 and similarly. I haven't checked. We have obviously need to guarantee this is greater than 0. Otherwise, you cannot try to convolute larger than signal, larger than input kernel on an input. That is of course. So let's just do here. Actually, we can let it to be a variable and call that the size of the output. But it seems that we only used it here and here, so we just repeat. It's fine. Then this S we keep it, and here that's the size of the kernel, kernel H, and kernel width. Let's look now. Yes, we have the dynamically sized kernel, and let's calculate LB. So we reallocate W because we have set up the random seed. It should give us exactly the same W as we have used before. And here is how we calculate the output function L using W, using B. Well, then we put this back. We use here maybe. When given A, we calculate the B using A, and correspondingly we use this L B B. So use this function. Okay, this will make it as a layer-wise computation, and the L will be LA A, and LB would be W clone. Put it here maybe. So the relevant elements are prepared together. So now this computation of DA we do not need to explicitly do that. After preparing the padded DB padded, we will be able to compute DA using the convolution. Let's just try that DA. Let's call that 2 for now because we want to have a check with the previously computed DA. Let DA2 to be convolutional 2 between DB padded and the kernel K, but we need to flip the kernel from the beginning here to the end. So we this would be 3, and the step size is -1. So let's just do this. Oh, we got so that will be -1, 0, from -1 to 0. Oh, still to get gives me the step size must be greater than 0. I think that is a torch thing. Let me do this. Import numpy as npy k npy equals k dot numpy, and let's see what we have. Now this is knp, and let's do. I think numpy understand this stuff better. Well, okay. So what we need to do? We just do this and turn it back to a tensor. Okay, I didn't notice that Torch does not provide this kind of indexing. Torch.tensor. Don't need this. K flipped. Does it work? Okay, at least once tried in the making a copy. Okay, copy. Got it. Flipped. Fine. Does that work? Yes. And this one? Yes, fine. Look, for this kind of stuff, you need to you need to know how it you need to know how it was motivated to understand it actually. Yes, I just put a comment here to use numpy for negative indexing to flip. Okay. Here we will use key flipped. Actually, it would seem a little bit weird for our stick to using a torch to do all this stuff, but without actually using the functionality of torch. But later we will learn that for this kind of computation, torch can provide us very easy functionality to perform all the calculations from higher abstraction level. All those operations could be done in one line. But of course, by implementing themselves, those operations from scratch provide us a great way to understand how convolutional neural network works. So let's do this and check how DA2 works. Okay, DA2. So maybe we need to compare that to DA. Exactly the same. We are happy. Now we have put everything together. Now we are ready to calculate the derivative with respect to the kernel weights.